Hello everyone. Now as a part of our learning on reservoir simulation or reservoir modeling or well modeling, now we will learn about PVT modeling and PVT analysis, fluid characterization, and we will do that in software called PVTP. It's another product of petroleum experts. It is, I think, one of the most popular softwares that are used to perform PVT modeling. All right. Maybe you can name several other software, but at least for me, it is one of the most useful. Okay. So in this video, we will construct a PVT model, a compositional model. Okay. And we will take the material from the PVTP itself. Okay. Here, as you can see, we have several tabs: file, options, data, calculation. And let's go to the help, index, maximize, open the work examples. Here we have characterization examples and EOS. EOS is equation of state application. Okay, open the drop-down menu. Now in this video, I will talk about this example one for oil characterization, and we will cover as many sections as possible. So please note that maybe this video will be quite long, okay? But I hope it will be quite comprehensive. I hope we can learn many things together. Okay, so yeah, I will go to the PVT and then go back to the help, and then I will read the messages. So yeah, I hope you can follow and let's learn together. Okay, so this is the introduction. Example one, oil. I will read, okay? I will read it out loud and you can follow and let's learn. Okay, this guide intends to demonstrate the thinking process behind characterizing a fluid, in this case an oil with PVTP. Okay, it should be noted that this is not a guide of the essential steps for matching any fluid. This is because every fluid is different, has its own challenges, and by definition, there are multiple solutions as well as pathways to particular solution. Okay, okay, we got that. Now the scenario. An oil reservoir in the extensive Logi Mill field has been discovered. A fully integrated model is to be built to come up with a development strategy. This integrated model is to be comprised of a numerical reservoir model, well and surface network models, as well as a process model. Okay, so you have process reservoir model there, well model, surface network model, and process model. Additionally, the likelihood of flow assurance issues such as hydrate or wax formation is to be investigated, and therefore the use of an equation of state, EOS, rather than a black oil description of the reservoir fluid is required. Okay, a fluid sample was taken and analyzed in a laboratory. The engineer has been tasked with using the lab data to develop an EOS description of the reservoir fluid using PVTP, and we are the engineers. Okay, so that's for the scenario, and we go to workflow summary. It's quite long. I will not read it out loud. So let's just check workflow summary. So we have QC lab report. Okay. We will define pure components. Oh, sorry. We will QC the lab report. We will define the pure components. We will define the pseudo components. So they are different, the pure components and pseudo components. Okay. And then lab data entry, we will input the laboratory data. We will perform regression to obtain a match model. And then we will do validation, and let's check the EOS application. Okay. So from workflow summary, now we will check the data available. Data available. The following data is at the engineer's disposal. Okay, so we have this data: fluid composition, constant composition expansion or CCE experiment, differential liberation or DFLIP experiment, and separator SEP experiment. Okay, now reservoir conditions. So we have reservoir pressure, we have reservoir temperature, and the depth of the reservoir. Okay, got that. And these are the units. So we will use field units. Okay, recombine composition. Okay, so this fluid is actually a recombination fluid, and this is the recombine composition. We have nitrogen down through C20 plus. Okay, so from nitrogen to C19, they are pure components. But C20 plus, it's not C20 pure. It's C20, C21, C22, and so on and so forth. And we combine all of these heavy components starting from C20, okay, all the way to the C heaviest, I don't know what it is, C heaviest, C20, all the way through the heaviest component. We will combine them and we call them C20 plus. And this component is a pseudo component because it's not pure component, okay? And mean molecular weight of C7 plus fraction is 220 gram per mole, okay, from C7 all the way through C plus plus. Mean specific gravity, okay, 0.87. So that's the recombined composition. Now let's check the CC experiment. Okay, so we have CC experiment. In this case, we have pressure against relative volume, okay? And then we also have oil density and then oil viscosity, okay? This is the reservoir pressure and the saturation pressure is 2091. Okay, got it. Now we also have differential liberation experiment data. In this case, we have pressure, oil density, solution GOR or RS, and oil formation volume factor. And separator experiment, okay, we have this stock tank gravity, API, and then we have SEP experiment 2, separator experiment 3. Okay. Now lab report quality check.